Welcome to the deep dive. Today we're plugging into a topic that, well, powers pretty much everything, current electricity.
That's right. We've got some really good educational material here to help us unpack it.
And our goal isn't just, definitions. We want to really get a feel for the fundamentals, how it all works, and why it matters.
Exactly, because understanding this stuff, it really opens the door to other areas, like electromagnetism.
Okay, let's get started. So, electric current. What are we actually talking about?
At its most basic level, it's the flow. The directed movement of free electrons through a material, usually a conductor, like a wire.
Like a tiny river of electrons?
Yeah, that's a good way to think about it. A river of negative charge.
But what makes the river flow? They don't just start moving by themselves, do they?
No, exactly. You need a couple of things. First, a conductor, and second, a reason for them to move. That reason is usually a difference in, let's call it electron concentration.
Meaning, like, more electrons in one place than another?
Precisely. Electrons are negative, so they'll naturally move away from an area where there are lots of them, a surplus, towards an area where there are fewer at a deficit.
So if you connect those two areas with a wire...
The electrons flow. They try to even things out. That flow is the electric current.
Okay. And how do we measure how strong that flow is? Is it just counting electrons?
Well, not individual electrons. That'd be impossible. Instead, we measure the total amount of charge that flows past a certain point in the wire over a specific amount of time. That's the strength of the current.
Right, the rate of flow. Is there a formula for that?
Yep, a nice simple one. IQ/QT. I stands for current, Q is the charge, and T is the time.
IQT. And the units.
Charge Q is measured in coulombs, that's a capital C. Time T is in seconds, S. And the current I is measured in amperes, capital A, often just called amps.
So 1 ampere is 1 coulomb of charge flowing past a point every second.
Exactly. 1A equals 1 C's. Perfect.
I've also seen things like milliamperes and microamperes mentioned. Are those just smaller versions?
Yeah, absolutely. In electronics especially, the currents can be really tiny. So we use milliampere, MA, which is 1,000th of an amp, microampere, a millionth, even nano NA and pico, PA, which are billions and trillions. It just makes the numbers easier to handle.
Right, keeps things manageable. And the charge on just one single electron must be incredibly small then.
Oh, it's minuscule. About 1.6 times 10 to the power of minus 19 coulombs.
Wow. So you need a huge number of electrons flowing to even get 1 amp of current.
A truly astronomical number, yes.
Okay, so if we want to measure this current in a real circuit, how do we do it?
We use a device called an ammeter. You have to connect it in series.
In series, meaning it has to be part of the main path, right? So all the current flows through it.
Exactly, like putting a water meter right in the main pipe. The ammeter has terminals, positive and negative, and you need to connect them the right way around, matching the power source.
Got it. Now, the source material also had a bit of a warning, a do-you-know fact about safety.
Ah, yes. That's really important. Even relatively small currents can be dangerous. Something around 0.2 amps, if it passes through the heart, can disrupt its rhythm and potentially be fatal.
0.2 amps. That doesn't sound like a huge amount given we talk about household circuits having several amps.
It's not huge, but it's enough to interfere with the body's own electrical signals controlling the heartbeat. It really underlines the need for caution.
Definitely. And it also mentioned electricity itself isn't renewable or non-renewable.
Right, electricity is a form of energy, but we generate it using primary energy sources, which can be renewable, like solar or wind, or non-renewable, like coal or gas. Electricity itself is more like an energy carrier.
That's a good distinction. Okay, let's try applying that I equal QT formula. Example 1, 6 coulombs flow in 3 seconds. What's the current?
Okay, IOQT. So I will 6 coulombs divided by 3 seconds. That gives us 2 amperes.
Simple enough. Example 2 flips it. 5 amps flow for 12 seconds. How much charge?
Right, so we rearrange the formula. QI times TQ, 5 amps times 12 seconds. That's 60 coulombs.
Okay. And example 3 asks for time. 20 coulombs need to flow to make a 4 amp current. How long?
Rearranging again. T equals QI. So T coulombs divided by 4 amps, which is 5 seconds.
Great. That really cements the relationship. Now, the material moves on to electric potential and potential difference. This sounds a bit more abstract.
It can seem that way, but it's crucial. Think of electric potential as kind of like electrical height or pressure at a point. It's what determines which way charge wants to flow.
So it related back to the electron concentration we talked about?
Exactly. An area with lots of electrons, that surplus, is considered to be at a lower electric potential. An area lacking electrons, the deficit, is at a higher electric potential,
Wait, lower potential with more electrons? That seems backward.
It does seem counterintuitive at first, but remember, electrons are negatively charged. They are repelled from areas of low potential, lots of negative charge, and attracted towards areas of high potential, less negative or even positive charge.
Ah, okay. So electrons naturally flow from low potential to high potential?
Correct. That's the actual physical movement of the charge carriers in most circuits.
But then there's this thing called conventional current, which apparently flows the other way. High potential to low potential? Why?
Yes. That's a historical convention that stuck. Before electrons were discovered, scientists assumed current was the flow of positive charges, and positive charges would flow from high potential to low potential.
Like rolling downhill.
Exactly.
Yeah.
So even though we now know it's mainly negative electrons moving from low to high potential in wires, circuit diagrams and analysis almost always use conventional current, flowing from positive high potential to negative low potential.
So in a battery circuit, electrons leave the negative terminal, go through the circuit, and enter the positive terminal.
Correct.
But when we draw the arrow for current I on the diagram, we draw it going from the positive terminal through the circuit to the negative terminal.
That's exactly right. It's just a standard way of representing it that everyone uses for consistency.
Yeah.
It works mathematically. You just have to remember what's physically happening with the electrons versus the convention we use.
Okay, I think I get it. It's a bit weird, but okay. The material mentioned a galvanometer here too.
Yes, a galvanometer is a very sensitive instrument. It can detect tiny currents, but crucially, it can also show you the direction of the current flow. Useful in experiments.
Right. Now, what about potential difference? How is that different from just potential?
Potential difference, often called voltage and symbolized by V, is simply the difference of electric potential between two specific points. It's the electrical pressure difference that pushes the current between those points.
So it's not just the potential at one point, but the change in potential from A to B?
Precisely. And it's directly related to the work done to move charge between those points. The formula is V equals W over Q.
Yeah.
V is the potential difference, W is the work done in joules, and Q is the amount of charge moved in coulombs.
So a bigger potential difference means more work is done per unit of charge moving between those points, or it provides a bigger push.
Both are true. A higher potential difference drives more current, all else being equal. The unit for potential difference is the volt, symbolized V.
And 1 volt is?
1 volt is the potential difference between 2 points when 1 joule of work is done to move 1 coulomb of positive charge from one point to the other. So 1 V equals 1 JC.
Got it. And like amps, there are bigger units? Kilovolts?
Yep. Kilovolts, kV for thousands of volts, megavolts, MV for millions. You see those in high-power transmission lines, for instance.
And how do we measure this voltage, this potential difference?
With a voltmeter, and unlike the ammeter, a voltmeter is connected in parallel.
Parallel, meaning across the component you want to measure, not in the main path.
Exactly. If you want to know the voltage across a light bulb, for example, you connect the voltmeter terminals to the points just before and just after the bulb, parallel to it. Again, polarity matters connect positive to the higher potential side, negative to the lower.
Okay, ammeter in series, voltmeter in parallel. That's a key difference. Oh, and the text mentioned voltammeter versus voltmeter. What was that about?
Yeah, that can trip people up. A voltmeter, small m, is the instrument we just discussed, measuring potential difference. A volt ammeter, capital A sometimes, is an older term for a device, an electrolytic cell, used to measure the quantity of electricity by chemical means. Totally different things, just similar names.
Good to know. Avoid that confusion. And LEDs were mentioned briefly.
LEDs, light-emitting diodes, yeah. They're just a good example of needing a certain potential difference, a certain voltage to turn on and let current flow to produce light. They're very efficient, don't need much current or voltage compared to old bulbs.
And the path the current takes through the LED or whatever, that's the electric circuit.
That's right. The complete loop or path that allows the current to flow from the source through the components and back to the source.
Okay, let's try the potential difference examples. Example 4. 60 joules of work move 12 coulombs. What's V?
All right, V equals WQ. So V equals 60 joules, 12 coulombs. That's 5 volts.
Example 5. How much work W to move 15 coulombs across 3.2 volts?
Okay, rearrange to W as VXQ. So W equals 3.2 volts times 15 coulombs. It's 48 joules.
Great. So ammeters and voltmeters, again, just a bit more detail.
Right. The ammeter, symbol A in a circle, measures current in amperes. connected in series. It needs to have very low internal resistance itself so it doesn't significantly block the current it's trying to measure. Connect positive to negative relative to the source.
Makes sense. And the voltmeter?
Symbol V in a circle measures potential difference in volts.
Connect it in parallel across the points you're interested in.
It needs to have a very high internal resistance.
High resistance. Why?
So that very little current actually flows through the voltmeter itself. You want to measure the voltage difference without significantly changing the circuit by drawing much current away from the component you're measuring. And again, polarity matters, positive to higher potential, negative to lower.
Low resistance ammeter in series, high resistance voltmeter in parallel. Got it. Now, electrical resistance itself. This is the opposition.
Exactly. It's the property of a material that hinders the flow of electric current. Think of it like friction for the electrons.
What causes this friction?
On a microscopic level, as the free electrons try to move through the material, they constantly bump into the atoms of the conductor. These collisions slow them down, impede their progress, and transfer energy, which often appears as heat.
So different materials have different amounts of this bumping?
Precisely. Conductors like copper have atoms arranged in a way that lets electrons pass relatively easily low resistance. Insulators like rubber or plastic have structures that make it very difficult for electrons to move very high resistance.
And the physical shape matters too, length and thickness.
Absolutely. Think about it. A longer wire means electrons have to travel further, so they'll encounter more atoms, more collisions. Longer wire means higher resistance.
Okay, longer equals more resistance. What about thickness?
A thicker wire is like a wider pipe. It gives the electrons more room to flow, more parallel paths within the material. So a thicker wire means lower resistance. It's easier for the current to get through.
Right, so resistance increases with length, but decreases with thickness or cross-sectional area, and material type is key.
Those are the main factors, yes.
And the unit for resistance?
That's the ohm, named after Georg Ohm. The symbol is the Greek letter omega, A. Looks like a little horseshoe.
For ohms. Okay. The material also reminded us again. Current flows from high potential to low potential until things equalize.
Yep, that fundamental drive to level out the electrical pressure difference.
And it said higher potential difference means more current. That seems intuitive now.
It is. A bigger push results in a faster flow, assuming the resistance, the opposition, stays the same. It's like turning up the water pressure.
The analogies helped there. Let's revisit them quickly. The heat analogy.
Yeah, that compares potential difference to temperature difference. Heat flows from hot to cold, right, until temperatures equalize. Current flows from high potential to low potential until potentials equalize. And a bigger temperature difference means faster heat flow, just like a bigger potential difference means more current.
Okay, that works well. And the water analogy. 2 tanks connected by a pipe.
Right. Imagine 2 tanks, X and Y, different water levels. The difference in level is like potential difference. Open the pipe between them. Water flows from higher level to lower level. That's the current. The rate of flow depends on the level difference.
And the resistance.
The pipe itself. A narrow pipe restricts the flow high resistance. A wide pipe lets water flow easily low resistance. It nicely shows how the difference drives the flow, not just the total amount of water, and how the path affects the rate.
Yeah, those analogies definitely help make it less abstract. Which brings us to the big one, Ohm's law.
Ah, yes. Absolutely fundamental. Ohm's law ties together the 3 key quantities we've been discussing. Potential difference, V, current I, and resistance.
Okay, what does it state?
It states that as long as physical conditions like temperature stay constant, the current flowing through a conductor is directly proportional to the potential difference across its ends.
Directly proportional. So double the voltage, double the current.
Exactly. If the resistance doesn't change, we write this as VI.
And the equation form.
We introduce resistance R as the constant of proportionality. That gives us the famous VIR. Voltage equals current times resistance.
VIR. Simple but powerful.
Incredibly powerful. It lets you calculate any one of those quantities if you know the other two. It's used constantly in circuit analysis and design.
And we can define the ohm using this law too.
We can. If you rearrange it to RVI, you can see that 1 ohm, 1 I is the resistance of a component when a potential difference of 1 volt, 1 V across it causes a current of 1 ampere, 1 A, to flow through it. 1 A equals 1 V, 1 A.
So it also shows that for the same voltage, if you have higher resistance, you get lower current.
Precisely. They have an inverse relationship when voltage is constant.
Okay, let's run through the Ohm's law examples quickly. Example 6. 6 volts gives 0.5 amps. What's R?
RVI equals 6V, V 0.5A equals 12 ohms.
Example 7. 12 ohm resistor, 6-volt battery. What's I?
I equals 6V12 equals 0.5 amperes.
Example 8. What voltage V is needed for 1.5 amps through 2.4 ohms?
VIR equals 1.5, A 2.4A equals 3.6 volts.
Okay, now a tuple with components. Example 9. A lamp on 230 volts draws 1 and 25 amps. Its resistance.
Our VI equals 230, V 8.5A equals 460 ohms. Quite a high resistance for that filament.
And example 10. What voltage for 2 amps through 10 ohms?
VC calls combining resistors. Things get more complex here.
A little, but there are clear rules. You can combine resistors in two main ways, series or parallel.
Okay, series first. How does that work?
Series means connected one after another, end to end, forming a single path for the current, like beads on a string.
So the current has no choice. It has to go through every resistor.
Exactly. And because of that, the current is the same through each resistor connected in series. That's a key point. And the total resistance.
It just adds up. The total resistance, our total, is simply the sum of the individual resistances. Our total equals R1 plus R2 plus R3 and so on. Adding resistors in series always increases the total resistance.
Makes sense, like making the obstacle course longer. What about parallel?
Parallel is different. Resistors are connected side by side. Imagine connecting all the left ends together at one point and all the right ends together at another point.
So the current reaches a junction and splits up, going through the different resistors simultaneously.
Precisely. It offers multiple paths for the current. Because of this, the potential difference or voltage across each resistor connected in parallel is the same. That's the key point for parallel.
Same current in series, same voltage in parallel.
Got it. How do you calculate total resistance in parallel? It's not just adding them up, is it?
No, it's a bit trickier. The reciprocal of the total resistance is equal to the sum of the reciprocals of the individual resistances.
Yeah, okay. Say that again.
1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3, and so on. 1 R total equals 1 R2 plus 1 R3 plus 7. Okay, so adding more resistors in parallel actually makes the total resistance smaller?
Yes, because you're providing more paths for the current to flow. It's like opening more checkout lanes at a supermarket. The overall flow of people current gets easier. The overall opposition resistance decreases.
Interesting. Let's try example 11. 5 ohms and 10 ohms combined. Series first.
Series is easy. Right, series, that's 5 plus 10 equals 15.
Now parallel.
Okay, 1R parallel is 15 plus 110. Common denominator is 10. So 1R parallel, 210 plus 110 equals 310. Now flip it back to find R parallel. R parallel, 103 ohms, which is about 3.33 ohms.
Wow, much smaller than either 5 or 10. Okay. Example 12. 3 resistors, 8, 12, and 24 ohms.
Rest series 8 plus 12 plus 24 equals 44.
And parallel.
1R parallel, it's 18 plus 112 plus 124. Common denominator looks like 24. So 1R parallel equals 324 plus 224 plus 124. 624 simplifies to 14.
Right. So 1 R parallel, 14. Flip it. R parallel alls 4. Again, smaller than the smallest individual resistor. That really shows the difference between series and parallel. Okay, next topic. The heating effect of current. We kind of touched on this with resistance.
Yes, it's directly related. Whenever current flows through anything with resistance, which is basically everything except theoretical superconductors, some electrical energy gets converted into heat energy.
Those collisions between electrons and atoms we talked about.
Exactly. The energy lost by the electrons in those collisions increases the vibration of the atoms in the material, and we perceive that increased vibration as heat.
The material described simple experiments like passing current through a wire.
Yeah, even a standard copper wire, if you pass enough current, will get noticeably warm. The second experiment used a light bulb, where the effect is much more dramatic.
Right, the filament glows white hot.
Because the filament has a much higher resistance than the connecting wires. So for the same current, much more energy is converted to heat in the filament, making it hot enough to emit light.
And this heating isn't always just a waste product, is it? We use it deliberately.
Absolutely. James Joule studied this effect carefully and came up with Joule's laws of heating. He found 3 key relationships.
Okay, what are they?
First, the heat produced, H, is directly proportional to the square of the current. I hope. Double the current, you get 4 times the heat.
Wow, the square. Okay.
Second, heat, H, is directly proportional to the resistance. Higher resistance, more heat for the same current and time.
Makes sense. And third,
Heat, H, is directly proportional to the time the current flows. Leave it on longer, it gets hotter, or rather, produces more total heat energy.
so putting it all together.
We get the formula. H equals current squared times resistance times time.
H equals IIRT. That seems pretty important for understanding heating devices.
It's the core principle behind electric irons, room heaters, electric kettles, geysers, toasters. Anything designed specifically to generate heat from electricity relies on this effect, usually by using materials with a carefully chosen high resistance.
Let's look at the electric light bulb example again. Tungsten filament.
Yes, the old incandescent bulb type. The filament is usually tungsten.
Why tungsten specifically?
Two main reasons. First, it has an incredibly high melting point, around 3,300 degrees Celsius. It needs to get extremely hot to glow brightly, so it can't melt easily.
Okay, high melting point. What else?
It also has a relatively high resistance compared to, say, copper wires. And according to HIRRT, higher R means more heat generated for the current passing through.
So it gets hot easily and can handle being really hot. Anything else? The text mentioned a thorium coating.
Ah, yes. Sometimes a coating of thorium oxide was added. It helps the filament emit light more efficiently at slightly lower temperatures, basically making it brighter and last longer.
So it's all about maximizing that heating effect in a controlled way to produce light. Fascinating how material science plays into it.
Absolutely. It's a great example of applying these fundamental principles.
Okay, we've covered a lot of ground in this deep dive. Let's try to wrap it up. We started with electric current itself, the flow of electrons.
Driven by a potential difference, or voltage, measured in volts, we use ammeters in series to measure current in amps.
And voltmeters in parallel to measure that potential difference. We also navigated the difference between electron flow and the historical conventional current.
Then we dug into resistance, the opposition to flow, measured in ohms, affected by the material, the length, and the thickness of the conductor.
Which led us straight to Ohm's law, V equal IR, the fundamental link between voltage, current, and resistance. We saw how useful that is with the examples.
And how combining resistors in series adds up, same current, and parallel, reciprocal formula, same voltage, changes the overall circuit behavior.
Finally, we looked at the heating effect, quantified by Joule's law, He also equal ITAR, and saw how it's used in everyday things, like the filament in an electric bulb.
It really forms the bedrock for understanding how so many electrical and electronic devices work. And as you said earlier, it paves the way for grasping more complex ideas like electromagnetism.
Absolutely. So when you use any electrical device, maybe give a thought to that invisible stream of electrons, the voltage pushing them, the resistance they fight against, and the energy changing form. It's happening all around us, all the time.
It really is.
And maybe something to ponder for you listening. We talked about heating elements, thinking about ICSE. If you wanted to design an efficient electric heater, would you favor a very high resistance element drawing low current, or a lower resistance one drawing higher current for the same power output? What are the practical trade-offs, maybe in terms of safety or material cost?
Or looking ahead, how might breakthroughs in materials with near-zero resistance superconductors fundamentally change how we generate, transmit, and use electricity based on the very principles we discussed today?
Lots to think about. Thanks for joining us on this deep dive into current electricity.